So I'm Doug Natelson. I'm a faculty member here in physics and astronomy as my primary appointment. I've got appointments in ECE and materials science and nanoengineering, so I can take their students when the opportunity presents itself. So I'm going to talk to you today, and again, this is in fact an AI-generated image, but it's not teal and orange in the color palette. But I'm going to talk to you today about some work we've been doing over the last few years about light emission in atomic scale junctions. And by the way, I'm giving like different versions of this talk like 2 more times in the next 3 weeks. So if people have feedback about the talk, that's actually very useful. So as always, I have to start with the acknowledgement of the people who really did the work. The earlier part of the talk is going to be some work that was done by my former student Yunhuan Zhu and my former postdoc Longji Cui, who is now a professor at University of Colorado. And also some work done by my former postdoc, Xiaowei Yang. And then the most recent stuff has been done by my student Shusen and my student Ken. Shusen just graduated, and he is, basically in the next day or 2 flying to China to take a big job at Huawei. So, and our theory collaborators on this are this trio of folks from Universidad Autónoma in Madrid. They're kind of real experts on this plasmonics stuff. And here's some references, and this will pop up again at the end. And of course, I have to thank the people who actually paid for the work. Can you actually see my pointer?
Yes.
Okay, I could always do the. I can do this if that makes it better. Hard to tell on my screen here. The Navy helped buy a key piece of apparatus for this, which was extremely helpful. And the NSF and the Welch Foundation have been supporting different pieces of the work along the way. Obviously, please stop me if you have any questions. I'm always happy to answer questions. So I know this is kind of the Cavity QED gang, but I suspect many of you are already familiar with the idea of plasmons. So plasmons are a key component of what I'm going to be talking about today. Plasmons are the collective modes of the incompressible electronic fluid. And the bulk plasmons are usually introduced in an undergrad class somewhere where you imagine I've got a chunk of material and I'm going to drag all the electrons off to one side by a little bit, right? And leave behind the ions. And when I do that, of course, now I have surface charges at the 2 sides, the one with the excess of electrons, the one with the deficit of electrons. That gives you a restoring force, and you can do the the basic problem of the electrons are going to slosh back and forth. They're just going to oscillate. And if the resistivity was 0, these things would, and there was no radiation or anything, these things would oscillate forever. And you can compute the frequency that this happens. It's called the bulk plasma frequency, and it's proportional to the. It involves the carrier density. It involves the dielectric screening in the material. But the reason these things damp out, of course, is because the conductivity is finite, and something like that has an oscillating dipole, so it can radiate to the far field. So it can damp itself radiatively or non-radiatively. You can also have surface plasmons, where you can have some periodic modulation of the charge density, right? So I can have an excess of electrons here, a deficit of electrons here, and so forth. I can do this in a periodic way, described by some sort of a wave vector. And then this too will have a time dependence. It'll have a frequency response, and it will slosh back and forth. And again, this will damp itself as well. So why do you care about surface plasmons? It turns out that these things usually involve charge separation. And so if you have metal nanostructures, or at least highly conductive nanostructures, you can excite these things optically very often. You don't have to, but you can. If you look in the near field, the local electric field near the structure can be a lot larger by some frequency-dependent factor than the incident field from the radiation that you're using to kick your material. So this has been used and exploited in various ways. You can essentially use these plasmon resonances to create optical antennas, right? So here's some work from Lukasz Nowotny's group in Zurich. And this is from a very nice kind of review paper that was in Nature Comm, where you can have different, you can imagine this little dot in the middle as some sort of emitter. Could be a quantum dot, could be a molecule, something like that. And now it's coupled to metal rods, metal discs, metal triangles, an array of metal bars, right? These are optical antennas, is one way to think about this. So, you know, in the same way that this is a classic dipole antenna interacting with an electromagnetic wave, this might be the sort of thing that once upon a time you would have seen, you know, attached to your television or attached to your car radio. But the idea is that the wavelength of the radiation is really big, and you end up essentially concentrating, in some sense, the potential difference down to some very small region, much smaller than the wavelength. And so these are optical antennas in the sense that they can focus incoming far-field electromagnetic radiation down to the deep sub-wavelength scale, right? I mean, here's some sort of, you know, really nanometer scale gap, right? And you can go the other direction. You can also have some kind of an emitter, and you can have it broadcast to the far field. You can effectively couple it well to the far field if you've got your little emitting dipole or whatever it is, your emission source, coupled to something that talks well to the far field. All right? So in my group, over the years, way back when, I was very interested in doing electronic transport measurements between extended electrodes, so things that, you know, kind of look like this, where you'd have some sort of electrodes and you have a nanoscale gap between them, and you'd want to put something in there and measure its electrical conduction. And one of the things that was a hot topic to do this on, you know, if you go back 15, 20 years, was doing measurements on one or a few molecules. And one of the big challenges with these molecules was always knowing, how do you know in your tiny little nanometer scale gap between your electrodes, how do you know the stuff you have in there is what you want? And it's not just some adsorbed goo from the air, right? That it's not just, you know, barbecue smoke from Houston that is kind of condensed onto your surface. Again, I'm sure you may not like to think about it, but you should know every single surface in this room is coated with a monolayer or a bilayer of like water and carbonaceous gunk, right? There's a reason people use vacuum chambers if they want clean surfaces. So I got into this question about what could you do with these, you know, I've already made the nanoscale electrodes. Maybe we could use them as an optical antenna and do spectroscopy on the molecules that are right there in the gap. And the idea behind this is, so here's a gap that we made by a process called electromigration, where you start with a continuous metal wire, and you decorate, in this case, we decorated the surface with molecules that chemically like to stick to the wire. We then ramped the current through the wire, and it broke, right? And if you know what you're doing, and we can talk more about this, you're not melting it. It's momentum transfer from the electrons to the ions themselves. You're actually moving the atoms around. And this kind of, once you create a region where it's necked down a little bit, you basically get even higher current density, and so it tends to run away. And then you're able to break these things into discrete source and drain electrodes separated by some tiny, tiny gap. And what you can do is, if you've got molecules all over the surface, you can basically take a Raman microscope, take an optical microscope, set up for Raman spectroscopy, and you can look and ask, where do I see, you know, Raman spectroscopy is inelastic light scattering. You can ask, where do I see the Raman emission from the molecules? And what you find is, before you make this gap, you see nothing, because the Raman cross-section is very small. And even though there's molecules everywhere, you can't really see them. But once I make the gap, I suddenly get emission from a diffraction-limited spot right where the gap is, right? So it turns out Raman scattering, remember I told you there's this field enhancement factor. If I shine light on these things and I'm at the wavelength that corresponds to some kind of a local resonance of these little gaps, the local field is enhanced by some factor G over the incident field, and it's a frequency-dependent factor. So if omega is the incident frequency and omega prime is the scattered frequency, it turns out the Raman scattering rate goes like G at the incident frequency squared times G at the scattered frequency squared. And if the resonances are broad enough, this is really like all the same number. So it sort of goes like incident electric field to the 4, right? So it's not hard to get a field enhancement factor of like 100, which means the Raman scattering rate is enhanced by 10 to the 8. And now suddenly you have the ability to see single molecules, right? So this is pretty exciting. This has been known for a while now. And one of the things we did, just to give you a sense, you know, we were doing this a while ago, you can look at Raman spectra of a little junction as I ramp the source drain voltage across the junction. So I drive current through the junction. And what you find is that by doing clever things, looking at the Stokes scattered light and the anti-Stokes scattered light, you can actually watch specific vibrational excitations turn on. As soon as my source drain voltage is big enough to excite, so in this case, there's a particular mode where if you look at where it's happening, it's this one out here on the edge here. It's happening at about 1800 wave numbers, which is about 0.2 volts. And a little under 0.2 volts. And so the intensity of this mode is constant, 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 constant. And then once my source drain voltage is big enough that it exceeds 0.2 volts, now I see that vibrational mode, the intensity of that mode picks up because I'm vibrationally exciting it with my tunneling electrons, right? So this is a lot of fun. And we did this in a few different systems. I'll get to some more cavity QED type stuff in just a second. But we had a lot of fun with this. And then we also started, when we were doing this, we also started playing around with, you would see that the vibrational modes of the molecule were varying in energy. The vibrational energies were changing with the bias you were applying, right? It took us a while to figure this out. There are things like the Stark effect, where you just imagine you're polarizing the molecule. The electric fields are pretty big. So you're applying something like 0.5 volt across a nanometer. So these are very large electric fields. So in the end, we realized that this is a combination of things. It really is kind of Stark physics, but also if you think of your molecule as having some molecular levels, electronic levels, as you dial the voltage around, you're actually slightly changing how much charge is on the molecule. And so you're affecting the charge transfer between the molecule and the electrodes. So what this means is if you think about chemistry at all, if I've got like antibonding orbitals, and you imagine adding population to antibonding orbitals, it makes the bonds weaker, right? And so the modes get softer, so you can actually see these things curving around. Anyway, let's talk a little bit about the gaps, okay? So in order to understand these gaps, it's useful to think about something called plasmon hybridization. So you all know what hybridization is. Hybridization is really if I take resonators and I couple them together, I can now have new normal modes, right, from my coupled oscillators. So the famous, the classic freshman physics example, I've got a mass on a spring, and I can couple two of them together, and then my new normal modes are going to have, instead of the single mass having the angular frequency squared of k over m, I'm going to have two normal modes pop up. I'm going to have the symmetric version where both of these things move, and the frequency is lower because the effective mass of this thing is now 2m, right? And I can have the anti-symmetric mode, where it turns out the frequency is higher. These things are oscillating against each other. So I've got, in some sense, it's like a bonding and an anti-bonding orbital, if you want to think of it that way. So our colleague, Peter Nordlander, and his, at the time, outstanding postdoc, Emil Prodan, here at Rice, had the insight that actually you can think about plasmon modes this way, too. And so if you really want to understand, I've got some weird metal structure like one of Dr. Hallis's nanoshells, and I want to understand its modes, I can really think of it as really a hybrid between a solid sphere and a void, right? And you can actually work out quantitatively what the resonances should look like. So this is a very useful idea. So it turns out if you go and you look at these junctions and you zoom in, here's an example of a junction made by a slightly different technique, but you can see here it is. You notice it has, by the way, no nice symmetries, right? It's very, very tough to control. This will come back later. It's very, very tough to control precisely down to nearly the atomic scale. It's very hard to control exactly what these junctions look like, almost no matter how you make them. But the point is that here is some sort of funny little geometry. And you can use something like COMSOL, this nice finite element electromagnetic solver, to ask what are the resonant modes of this structure, okay? And it turns out that when you break all these symmetries, things get very complicated. So this metal strip, we have chosen the width of this metal strip and the thickness of this metal strip so that there is a transverse dipolar resonance at about 785 nanometer free space wavelength, because that's the laser we have. And ordinarily, so if this junction was like two perfectly squared off rectangles, that would kind of be the end of the story. There would be this dipole resonance with the polarization this way, and then there'd be other resonances, there'd be some kind of dipolar resonance the long way as well, but that would be at lower energies because it would be sort of redshifted by things. And any other higher order multipole things happening in this junction would be dark because they wouldn't have any dipole moment. You'd have quadrupole, octopole, so forth. But once you break the symmetry, these things all talk to each other. So you can have these highly, highly localized field concentrations where that mode, that plasmon mode, actually picks up a piece of this dipolar character. So you can now optically excite it. And it can couple to the far field. It is always interesting, when we first started trying to do these spectroscopy measurements, I had a couple of different people tell me this was never going to work. And the argument was reasonably persuasive, which is when people have done lots of stuff with nanoparticles. And basically, if I make the nanoparticles bigger and bigger and bigger, retardation effects set in so that if the size of the nanoparticle becomes such that like the far end of the nanoparticle doesn't know what the end near the gap is doing, you kind of lose all of your nice resonances, right? And it's true, you lose like the discrete like dipolar or quadrupolar resonances of the individual particles. But it turns out that it's this sort of thing that totally saves you, right? So you actually can have these big extended electrodes that go off to infinity, so you can hook wires up to them, and still have very interesting local mode spectra. Okay. So questions occurred to us, right? Can we exploit these modes? If we can drive current, maybe we can turn this around, and this is what we've been doing in recent years. We can turn this around, drive current through this thing, and see if we can get light out. Talk about the physics of that in a second. And another thing you might think about, directly relevant to this group of people, can we use these ultra-localized modes as some kind of cavity for strong light matter coupling? So let me say a little bit about the cavity aspect of this, right? So, obviously, if you're sitting in this room, you've probably already heard, multiple people talk about this before. But, the rate of optical processes, if you just do like a Fermi's golden rule kind of argument, the rate of quantum mechanical optical processes often depends on the density of states, the availability of final states for your photons. And Purcell had this, E.M. Purcell, who got the Nobel Prize for helping to develop NMR, had this fantastic insight that, if I have a cavity, the density of states for photons is very different than what it is in free space, right? If I have a cavity, I've got one cavity mode per whatever the bandwidth of my cavity is, instead of like this whole continuum of free space modes. How many people here have actually looked at this reference? Okay. Those who do, what's the most remarkable thing about this reference? If you actually look at it, it's not even a page. It's like a good paragraph. Yeah. Yeah, it's good to have like a paragraph that gets cited like 8,000 times. You're doing pretty well if you can do that. Okay, so there's this thing called the Purcell factor, where essentially the Purcell effect, the thing Purcell was thinking about was really microwaves, and he was thinking about nuclear transitions because he was doing NMR. But the general idea is I can enhance the decay rate for spontaneous emission, which ordinarily you think spontaneous emission, this is like given to you by God. But really, it's given to you by God in the sense that God gives you the density of states for photons in free space. If I mess with the photons in free space, then even the spontaneous emission rate gets changed. So Q here is the quality factor of the resonance, right? V is the mode volume, and you can define that by sort of like integrating up where the intensity is and deciding roughly what the spatial extent of the intensity is. So in principle, these plasmonic resonators are cavities. Now you do have to be careful, right? So local surface plasmon resonances, they have poor Q, right? So you'll see all the plasmon resonances I'm going to show you have a Q of like 10 or 20. So this is terrible for a cavity, right? But the effective mode volume is really tiny, right? So if I'm using 785 nanometer incident light and my gap is like a nanometer, I'm confining things to like wavelength over 700, right? So this is very, very tightly confined. So your mode volumes are really, really, really small. So you can still have in principle, have a big, Purcell type enhancement of processes. By the way, I should point out this paper has also been cited a few hundred times. There really are some subtleties about treating plasmon resonances as cavities. because what you really have to be careful about is that the permittivity, the dielectric function, can basically go to 0 or go negative. And so when you have to think very carefully about how you define mode volumes when you're sitting at a resonance of one of these structures. And honestly, I'm not sure I could give you a detailed explanation of that if you made me. Okay. Yes. Do you have a question?
Yeah, the mode volume, is that dl or dl cube that should be?
This is the vector. This is meant to be d cubed r. Yeah. I literally copied this from the paper that discussed this, and you're right. That should be a d cubed r if I'm being good about my notation. It's bold, so it's a vector, but this makes it look like it's a line integral or something weird like that, right? And it should be a volume integral. So, okay. So the structures we make, let's not worry about molecules. We're not going to worry about molecules for the whole rest of this talk, basically. They're basically tunnel junctions, right? I'm going to make two pieces of metal so close together that the wave function of the two sides spill out, and I can get some kind of tunneling conduction from one electrode to the other. That means, by the way, that at their closest point of separation, they're something like a nanometer apart. The gaps are genuinely small. I will say, when you make these things, and Ken could tell you, when you make these things, if you migrate them, you get these tiny junctions, and if you raise them up to room temperature and you wait a little while, they become the resistance becomes immeasurably large, because basically the metal ends just kind of reconstruct and kind of spread apart, and your tunneling gap becomes this big, and you can't tunnel anymore. So the history of light emission in tunnel junctions goes back a long way, back to the halcyon days when Ford Motor Company had a serious research lab. So here's the conventional picture. Here's my filled electronic states on one side, here's my filled electronic states on the other, and this is my tunneling region, and I'm going to basically, most of my electrons just elastically tunnel from filled states over here to empty states over here. But if I have a local plasmon mode that lives somehow at this junction that we can couple to, then it's possible, if my bias is big enough, that my electrons can inelastically tunnel. They can dump energy into this plasmon mode and still end up in an empty state on the other side. And the idea is that some of these plasmons decay radiatively. Remember I mentioned before this idea that things with oscillating dipoles can certainly emit photons, right? So you can have this collective sloshing of electrons that can radiatively decay. It can just stop and spit out a photon. Now, with this single electron at a time process, the highest energy photon you're ever going to get out is basically the size of the bias you apply, right? Because that's the amount of energy you have to play with. And you can fudge this a little bit by kT, where your Fermi functions are smeared out by kT, but you can't fudge it too much, okay? But where things start to get pretty interesting is people noticed, so with the advent of scanning tunneling microscopy, this whole field of light emission in tunnel junctions had a real renaissance in the early 21st century, certainly. And people started noticing, if I make the conductance pretty high, so that the currents are pretty big, then what you see are, you don't just see single electron processes anymore. You see photons coming out with energies higher than the bias you're applying. Now, you're not cheating in any way. You're not, the emission efficiency is bad, right? So what's going on? The answer is that somehow you're taking the energy of two or more electrons and converting that into a photon. So there's different ways to do it. You can have kind of higher order, Auger-like things going on, like in this PRL from Abe Nitzen at the University of Pennsylvania. And the point is that when people, you can really talk about first order, second order, third order processes. So second order processes, there should be a cutoff for those at twice the bias you're applying. And these folks make the argument, I'm not sure how persuasive it is, that they see kinks in their data at twice the bias voltage. Okay. Now, something else that people noticed at this time, there's actually a deep connection between the radiation from these things and the actual noise, the fluctuations in the tunneling current. There's a deep connection there. And I don't intend for you to take much away from this beyond people can talk about, you can theoretically deduce, if I've got some small number of transmitting channels, you can calculate, and the conductance, you can calculate what the fluctuations in the current should be. And then you can relate what the radiated power is supposed to look like from the first order process, from the second order process, and so forth. One piece of evidence that this works is the claim is that when the conduction is given by one fully transmitting channel, so if basically you only have one channel to worry about and its transmission was 1, then the noise gets suppressed. So your emission should get suppressed. And this is a very pretty paper where, yeah, if you do, here's the light emission versus the calculated noise, right? And there's a suppression in the right spot. But the bottom line, here's the bottom line. If I give you the plasmonic spectrum, basically the mode shapes of the plasmons, and I tell you we're in the tunneling regime, then in principle, you have an analytic way of calculating what the emission spectrum should look like. Okay? Okay. Now, fast forward a couple of years, people noticed, and this is a group in France, Alexandre Bouhillier's group in Paris, noticed the following thing. Actually, if you've got really high conductance junctions, and he was doing things very similar to ours, here's a little false color SEM image of one of his junctions, you really do see, you don't see any sign of a cutoff at all at the bias you're applying. You just see kind of continuum emission, right? So there's clearly multi-electron processes happening, but there's no signs of cutoffs. And their idea was that what really is going on is you've got basically a hot electron gas. You've got hot electrons. You're creating hot electrons in this tiny little space at the tips of these wires. They're so hot that they're radiating. But the trick is they're not radiating into ordinary free space. They're radiating into whatever the plasmon modified density of states is. Right? So you're going to get something that's going to kind of look like the Planck spectrum, except it's not going to look like the density of states for free space. It's going to have this plasmonic density of states in it. Okay? So that's the idea. And it's going to go to the current as the current to some power. Right? And in principle, you could do a complete theory of this whole thing and calculate what that exponent is. But in practice, as I'll show you on the next slide, like we've looked at hundreds of junctions. And you can look at a whole bunch of junctions and you decide for yourself that alpha is about 1.2. Okay, which means rho has to have some kind of funny units to make this work, but that's OK. Right? There's some constant out here that takes care of the current dependence. All right? So here's a somewhat blurry SEM image of one of our junctions. Again, you can see it's pretty ugly, right? Definitely not very symmetrical. Has maybe, if you stare at it, you might decide it's got some level of even geometric chirality to it. But what we're going to do is we're going to apply a bias across this junction, and we're going to look at the light that comes out. And it really does emit. I mean, this is just a little cheap CCD camera, and you can take pictures of the light coming out of these things, right? So you can do, if you assume that this is I shouldn't point at my screen with my finger, that's not very useful. If you assume that this is the functional form, there's, Bouhillier et al. Pointed out there's an analysis you can do, right? What you can do is, first of all, if you think you're in the limit where you're kind of more like a Boltzmann factor than the full Planck, than the full Bose factor here, right? So if you're in that limit, you can take your data at different voltages. You can normalize your measured spectra to the spectra at some reference voltage. And you can deal with the currents as well. And if you plot the log of that, you should get something that, in principle, is a straight line versus energy. And the slope has to do with the effective temperature of your black body, of your electrons, of your heated electron gas. Right? So here's a bunch of spectra taken on a particular junction. Here's the bias voltages we're applying. And as you can see, all of the photon emission is happening at energies above the bias we're applying. And there's no signs of cutoffs or anything. There's a couple of nice bumps there. Right? So if you do this collapse analysis, what happens? Obviously, it works, or I would not be telling you this story this way. The normalized spectra really, on a log scale, really do look like straight lines. Right? You can back out effective temperatures from this, and they tell you that while the atoms are sitting still, and they're at the ions are at a comparatively low temperature of whatever you set your cryostat to, 30 Kelvin or something. The electrons right at the tips of the wires can be at like 1800 K, 2000 K, 2200 K. They get very hot. Okay, and you can really back out rho of omega. Like all of these curves really do have the same underlying shape, and it looks like this. the collapse is really, really pretty. Now, when I've been plotting these spectra, we've not been looking at their polarization at all. We've been looking at the unpolarized spectra. But you can select, you can have a linear polarizer, and you can choose which photons to look at, right? And what you find is that in this case, there's a big peak at low photon energies that's polarized this way. That's kind of that lightning rod dipole, interelectrode dipole kind of peak. And there's a big peak that's polarized the other direction, right? Transverse to the wire, and that's basically associated with these really, these modes that are hybridized with the strip, the transverse mode of the metal strip. And so what this means is you can make very pretty polar plots, right? You could rotate the polarization and look at the spectrum, and you could plot the height of the spectrum is the color, and then the angle is what the polarizer was pointing at. And so what you really see is, at low energies, the emission is polarized along 0, and at high energies, it's polarized closer to 90. Okay. So what is going on? How do we think about this, right? And this was actually a pretty fun investigation. So the light emission mechanism is from the hot carriers, right? But how are you really generating these hot carriers? And we were working with Peter Nordlander on this. Okay, I told you a long time ago, some carriers tunnel inelastically and they excite these plasmons. And before I told you that some fraction of those things decay radiatively. Most of them decay non-radiatively by Landau damping. So what does that mean? It means when they die, they make a bunch of hot electrons in holes. Now I'm only drawing them on one side, but these plasmon modes are delocalized over the two electrodes. So this is happening on both sides of the junction. It's just hard to draw. Okay, so these things create non-radiatively, decay non-radiatively, and what happens is these things can relax pretty quickly off of each other. They can scatter off of each other. And what you end up with is a tail of the electronic distribution that is quasi-thermalized at one of these very high temperatures. Okay? And then you can get radiative recombination of the electrons in the holes. It turns out usually you're combining an electron from one side of the junction with a hole on the other side of the junction because there's a lot more energetic phase space for that to happen. We sort of just really came to appreciate that very recently. But the point is, in this case, plasmons come into this problem twice. Plasmons come in on the generating the hot carrier side, and they come in on the radiating to the far field side. So this is very sensitive to the quality of the plasmons. Okay. The other thing I should point, and I'll show you data on that in just a second. What's the effective temperature? The effective temperature is really set by your bias, right? Because that's really what's determining what you can excite, right? So now the fact that I'm getting photon energies higher than the bias I'm applying isn't that surprising, because when you think about it, if I apply a bias of 1 volt, that's like 10,000 degrees, right? It's not that surprising that I should get some kind of emission that way. Okay. Let me see. Yeah, so we came up with this mechanism because it was a variant on something that Nordlander had done for photoluminescence, above threshold photoluminescence in nanoparticles. So how sensitive is this stuff to the plasmons? Really sensitive. So this is kind of a funny plot. This is log base 10 of the photon yield, applied bias, applied current, and you can kind of collapse these things down. And what you find is that the photon yield for pure gold junctions with no other metal in the problem is kind of almost 2 orders of magnitude higher than gold with a 1 nanometer thick chromium adhesion layer to keep the gold adhering to your substrate better. Right? So just mucking up the plasmons a little bit by adding in a little bit of that transition metal for the adhesion layer drops your light emission by an order of magnitude. So this really does tell you, the plasmons matter a ton, right? You can't explain this level of sensitivity to the quality of the plasmons unless they're coming into the problem twice. Okay. Just kind of some icing on the cake. You can do this with aluminum as well as with gold, right? So here's some aluminum. And the interesting thing about aluminum is that you can actually easily migrate it very gently. So that's good and bad. The original motivation for using aluminum was it doesn't have any interband transitions, so maybe we can do this in the blue, right? The problem is if you apply large biases, the aluminum atoms just move around because they're very light. But the point is I can start with a junction in this high conductance limit. get this above threshold light emission. The currents we're talking about are kind of 15 microamps, that level, right? You see high effective temperatures. You can do this exact same analysis and back out some weird looking plasmonic density of, photonic density of states. Okay, now I know that. Now I can break the junction more. And I can break it in a controlled way where I don't really grossly change its shape. I'm just moving around that last 1 or 2 atoms. And what happens is that now I should be able to go into the low conductance limit, and it totally works. Now you suddenly, this exact same device, migrated a little bit more. Now you see there's a close to a hard cutoff at the bias you're applying, right? And it's hard for me to tell how this looks on the screen. If you take this density of states, that rho of omega, and you take that the analytic expressions from before about if you assume you've got one dominant tunneling channel, and you can figure that out from the conductance, you can calculate what the spectrum should be, and that's what the dashed green line is in here. Like, it just works, right? So I think we really nailed this down. I think we really do understand the nature of the light emission process. The light emission process is very different if electrons are coming through and the next one's coming through before the energy from the last one had a chance to get away. You really can ratchet up your effective electron temperature. And if that's not happening, you go back into this sort of single electron picture, right? So I think we really do understand exactly how you get electroluminescence from these junctions. So let's get something a little closer to the kind of stuff you're thinking about. By the way, I am still very interested. There are certain things I would love to do in this kind of light emission stuff, where it would be interesting, for example, to do photon counting and really look at the statistics, because if you do photon counting, G2 of a truly thermal source is supposed to be 2. Turns out that's actually very, very hard to see. Right? The second order correlator being actually 2 is very hard to see. So I've got equipment to do this. It's just turned out to be extraordinarily difficult. Okay, so I want to talk about coupling these little modes to other things. All right? So you can couple plasmons to excitons, and you can create the terrible word plexiton, which has been coined in the literature by other people. But it's a way to study strong light matter coupling, right? So a lot of work has been done on this before, where you can do things like, here's my little bow tie antennas, and I can do scattering measurements. I can shine light on them and look at scattering spectra and see the resonances of my little bow tie. And then I can take a 2D semiconductor, like in this case molybdenum diselenide, and I can put that down on top of them. And what you find is, here is the blue curve is the broad plasmon resonance of this little paired triangle antenna. The gray curves, that's the A and B excitons of the MOSE2 by itself. Put them on top of each other, and what do you see? You see a split peak because now you've got some hybridization between the exciton mode in the 2D semiconductor and the plasmon mode of the metal antenna. And so you can look at, you can fit this, you can look at the width of this. If you could continuously tune this, you could get some beautiful avoided crossing, which people love to do. It's hard with these plasmonic things to tune anything in situ. But this is the kind of cavity QED type stuff that you all should be your bread and butter if you're coming to these talks. So we tried this, okay? But instead of shining light on the thing and doing scattering or photoluminescence, what we did was, here's the few layer tungsten diselenide on top of our device. And what you see is when you do the electroluminescence, there's a notch out of your device. There's a notch out of the emission spectra. And that notch is right on top of where the photoluminescence exciton peak is from the semiconductor. So we're seeing this. We're seeing some kind of coupling. And the exciting bit is that the split can be big. Right? So, and it's the biggest challenge, before I show you the next slide, I'll just say the biggest challenge is, remember the polarization dependence of the radiation is complicated from these junctions, even in the absence of the semiconductor. That's because the plasmon modes are kind of a mess, and every junction is different. right? Because the symmetries are broken differently in every one of these junctions. I would love to have microscopic control to make junctions that all look the same. And I've got some ideas on that, but it tends to be very challenging. So what you find is that you can really look at the splitting, and depending on what angle you're looking at, you can get really these deep splittings, right? You only see these kind of deep splittings when the TMD, when the semiconductor is on there. They're not there when it's not, right? So the understanding of this, what's really going on, and the fact, by the way, the collapse analysis still works for this, right? So the way to think about this is, and again, our theory colleagues, they worked hard, they did modeling, they can basically reproduce a lot of the features. But the bottom line is that what's going on is the same kind of electron-hole recombination as before in the metal. That's really where the photons are coming from, right? But the dielectric environment that this is happening in is really weird. It's in this dielectric environment where you've got these coupled excitations between plasmons and excitons, right? So again, everything is kind of strongly coupled together, so it doesn't make sense to think about just plasmons anymore. It doesn't make sense to think about just excitons anymore. But the bottom line is, this is actually affecting, so the coupling can be very strong. This is actually affecting how the energy is flowing in the metal, right? Like you're taking electrons and holes in the metal and making them recombine. And by playing with the dielectric environment, you are changing which energies prefer to recombine, which I think is kind of interesting, right? That is kind of a cavity QED-ish kind of effect. So, it's a matter of somehow microscopically playing with the dissipation of energy in these structures and whether the energy goes into heat or whether it comes out in the form of light. Okay. By the way, we also did this with, the collapse analysis still works, and we also did this with MOS2, just to, which is different semiconductors to make sure that the things are happening at the appropriate energies for that. Right. So, so what are we doing now? So one of the things that I thought was really neat was this PRL from a couple of years ago, where these people were basically taking, instead of hybridizing plasmons with excitons in a semiconductor, they decided to make high quality photonic crystal cavities and hybridize some kind of plasmon resonance. Here's a tiny little dipole antenna on top of some kind of interesting photonic crystal cavity, right? So this is something we're working on right now. I don't really have data ready to show you. We've got some intriguing initial results, but we can, bottom line, another student, a previous student, Keijin and Ken, can make these cavities. We can make the wires right on top of the cavities. We can basically try and do light emission coupled to, Q of 1,000 dielectric cavities, right? So it'll be interesting to see what happens there. So in the last few minutes, I know I'm supposed to leave some time for questions, I guess. In the last few minutes, let me tell you about something exciting and brand new. We just submitted the paper on Friday. It showed up on the archive last night. So what does magnetic field do to all of this? This is the gadget that the Navy bought for me, by the way, was the cryostat that allows you to apply magnetic fields to these kinds of structures and still do the optics. So classically, if I take a gold structure, right, or some other diamagnetic metal, not a magnetic metal structure, magnetic field should really not do much, right? Why not? Well, if you think optically, the off-diagonal terms in the permittivity are tiny, right? I mean, there's lots of work out there about magnetic circular dichroism and little plasmonic structures, and the effects are parts in 10 to the 3, okay? And the fact is that's because basically if you think about where is this coming from, like classically you've got carriers sloshing around in the metal, and the Hall effect, the curving of the carriers due to the magnetic field, it's just small in something like gold, right? The Hall angle is tiny, so you're just you shouldn't see much. And likewise, the Zeeman energy scale at any kind of fields you can achieve in the lab is, if you're lucky, it's a millivolt. And a millivolt is tiny compared to the photon energies we're talking about here. It's tiny compared to the biases you're applying. So you might naively think you won't see anything. And you can even do a calculation. You can do, this is a calculation by Alessandro Alabastri and his student Qianye. You can take an example of one of our type junction geometries. Here's some charged plus and minus charges, a little snapshot of the thing, right? And you can try and calculate like what would the optical absorption of that thing look like at 0 Tesla and at 6 Tesla, and I defy you to be able to tell the difference between the red curve, the red dashed curve, and the black curve, right? These things differ, but they differ at the parts in 10 to the 3 level, and you just can't see it with your eye. Well, this is why we do science. Surprise! Magnetic fields actually do a lot. Okay, so it's a little hard to read the legend here, but basically, this one, the blue one here, is at positive 6 Tesla. The kind of maroon one here is at minus 6 Tesla, and we get all kinds of evolution in between. And this, this peak changes by almost a factor of 2, right? Tens of %. So orders of magnitude bigger than what you'd expect. Now, what could do this, right? I just told you, you throw this thing into COMSOL and you simulate the classical electrodynamics and it doesn't do it. So that tells you it's got to be something to do with quantum mechanics that you're leaving out of your model, right? And in fact, you can do a plausibility argument. There's something called the magnetic length. You can just define a length scale associated with how much wave functions have to adjust themselves when you put on a magnetic field. And this order of magnitude, this magnetic length, is about 10 nanometers if you're at 6 Tesla. So it's totally comparable to a bunch of length scales in the problem, right? So it's not at all crazy that magnetic field might do something. So let's look at this in a little more detail. Here we've got, different. So we've seen this in a bunch of junctions. We've seen this we've done it fairly comprehensively in at least 9 gold junctions, and we've done it in one aluminum junction where I have a supplemental slide. The same sort of thing happens. So here we have so we do a bunch of analysis on one particular device just for consistency. Here's, at minus 6 Tesla, here's curves at a bunch of different biases. 0 Tesla, curves at a bunch of biases. Plus 6 Tesla, curves at a bunch of biases. You can do this collapse analysis. You can find what that density, this is all unpolarized. You can find what that density, rho of omega, what that plasmonic density of states looks like. And it's quite different for the different fields. So the fact that the collapse analysis works tells you it really, it is still the same basic idea about electron-hole recombination in some plasmonic density of states, but the modes that are relevant are different at different fields, right? You get, by the way, quite high effective temperatures in this particular device. If you want to look at the polarization dependence, I don't expect you to get much out of this except that the left column is at minus 6 Tesla, the center column's at 0 Tesla, the right column's at 6 Tesla. And as you can see, by the way, at 0 Tesla, at 0 degrees, which is in the middle, at 0 degrees you get a peak at at 90 degrees you get a peak at higher energies, at 0 degrees you get a peak at lower energies. That's the same thing that was true before. So this is 0, this is 180, this is 90. So that trend from before is still true. But what you can see is, as a function of magnetic field, these line cuts, they all look quite different. So something very wild is going on with the plasmon modes in this thing as I ramp up the magnetic field. And again, you can plot this as a polar plot. I don't know. We went back and forth. The polar plot's the one that is the figure that's in the paper, and the line cuts are in the supplemental, right? We went back and forth about what conveys more to the reader. Another thing is you don't have to detect linear polarization. You can detect circular polarization. And what you find is even at 0 field, there's quite a bit of circular dichroism, right? This thing is emitting circular. You can think of it as emitting circularly polarized photons. That's because the structure is chiral, right? There's some geometric chirality to the structure and to the plasmon modes. But again, everything changes quite dramatically with applied magnetic field, right? The bottom line, that I only have a couple of slides left. The bottom line is chirality of the structure and broken symmetry of the structure plus field basically ends up amplifying the ellipticity of the dipoles, and I'll talk about that in a second, the actual electron-hole transition dipoles. And if you don't have the broken symmetry and the chirality, it doesn't broadcast very well to the far field. But luckily, almost all of our junctions are quite messed up, so we get lots of efficient coupling to the far field. So what do I mean by these transition dipoles? So our theory collaborators, they played around, but actually they did this with COMSOL. I did not know you could solve the Schrodinger equation in COMSOL. But you just can imagine I've got two chunks of material. I can take a guess at what their wave functions kind of look like. I can do a toy model, right? So here's two displaced from each other triangles. You can't see it on this scale, but there's some amount of wave function overlap between the two sides. And it turns out you can compute. I can take a whole bunch of different states of, on one side, electrons on one side, holes on the other, if you will. And I can actually ask, what are the transition dipoles if I want to have an electron and a hole recombine? And you get something rather interesting. So the thing that's being plotted here is basically ellipticity. It's if something was +1, it would be completely circular. It would be like emitting completely circularly polarized light of one helicity. If it's -1, it goes the other way, and if it's 0, it's linear polarization. So in the absence of a field, no matter what goes on here in terms of shape, you don't get helical transition dipoles. But as soon as you turn on a field, you do, and some of them can be, even though you'd think that the responses should be small, there are certain modes that can have very big, certain couplings of wave functions that can give you big ellipticities, right? So big circular, big generation of elliptical emission just from turning the field on. So again, elliptical dipoles plus structural chirality equals B-tunable far-field emission, right? And you can actually, our theory collaborators, they made some toy model of a junction, and they can get things that act. The curve in the middle is the the solid curve is the zero field curve, and the two different kinds of dashes are -6 Tesla and +6 Tesla, and they can really duplicate the trend we see in the data if you play with the geometry. So that's it. That's kind of our latest very exciting result. Let me give you some conclusions. So I hope I've convinced you that electroluminescence in these kinds of structures can be a really interesting probe of light-matter coupling. Plasma and exciton coupling affects recombination of electrons and holes in the metal. So it's an interesting question. If we can tune things with cavities and other ways, can we also, in other ways, control and engineer the flow of energy at the nanoscale? The surprising new result, very new, is that B field really affects the light emission by a factor, more than 1,000 times, more than 100 times rather, what you would expect naively. And there's lots of interesting questions, things left to do, right? Can we see similar effects in coupling to dielectric resonators? Could we actually really control the geometry well enough to really, give us a new paradigm for tunable, in situ tunable nanophotonic devices, right? But again, just as you might imagine, one of the things that is I don't want to say it's a holy grail because that sounds weird, but one of the things that's interesting to consider is whether you can make an electrically pumped plasmonic nanolaser, right? All the people who take plasmons and couple them to emitters and make lasers, they're all optically pumped. And the question is, could you make an electrically driven plasmonic laser this way? That was a very small emitter. So I'll put up the acknowledgements again, and I'd be happy to take any questions.